So this is ELC 131, Circuit Analysis 1, and we continue on our discussion of alternating current. Now, when we define, describe, discuss all AC waveforms with respect to the x-axis, one of our fundamental measures or quantities is a cycle. And a cycle is merely the period through which the waveform repeats itself. So looking at the waveform that I've sketched on the board, one cycle is the period from here to here. When the waveform crosses zero going in a positive direction until the waveform crosses zero going in the positive direction again. So this period is one cycle. Now, we could also say that one cycle exists from the positive peak point to the next positive peak point. This is one cycle. Again, it's the period through which the waveform repeats. And one cycle can also be described as the period from here to here, the period through which the waveform crosses zero going from positive to negative until the waveform crosses zero again going from positive to negative. And for the waveforms that we'll discuss and in this presentation, we're always talking about what are considered periodic waveforms, which means that the time or the length of one cycle is always constant, regardless of where we begin and end our cycles. Now, in ELC 131, in the electrical and electronics classes, we will always define one cycle as taking 300 or being 360 degrees. Just like the circumference of the circle or a circle is 360 degrees. Now in math class, you'll define or describe one cycle as taking or being 2 pi radians in length. And major reason for this is that mathematicians don't like units of measure like degrees. They want all values to be numbers with no units. Now, looking at this waveform, again, one cycle is 360 degrees, so 1/2 of a cycle is, of course, 180 degrees. 1/4 of the cycle is 90 degrees, and 3/4 of one cycle is 270 degrees. And of course, we can break this cycle down into smaller angular distances if we need to. Now, in describing, quantifying, discussing these waveforms, we will quite often, instead of talking about this waveform in an angular distance on the x-axis, we'll talk about this waveform with respect to time along the x-axis. And I will always represent time with the time of one cycle with a capital letter T, so that we can differentiate that time measurement from an instantaneous value of time or some value of time along the entire x-axis. So the capital letter T in here will be used to represent the time of one cycle. Now, when, again, describing, discussing, quantifying waveforms, we'll also talk about waveforms with respect to their frequency. Frequency symbolized with the letter F, measured in hertz. The unit symbol is capital HZ. So mathematically, frequency is the reciprocal of time. So for example, if this waveform has a time of 16.67 milliseconds through one cycle, what would be the frequency of that waveform? Well, frequency is 1 over time. 1 over 16.67 milliseconds gives us approximately 60 hertz. And I picked this value, 60 hertz, because that is the frequency of the AC waveform provided in our homes at the outlets, the receptacles, and supplied to our lighting and appliance circuits. So again, we can talk about this AC waveform on the x-axis in the horizontal domain, first and foremost by defining what a cycle is, and that's simply the period through which the waveform repeats. And a cycle is always broken down into, or is always 360 degrees. We can talk about this cycle instead of in angular distances, we can talk about it in time. And we can talk about these waveforms with respect to their frequency, which is simply the reciprocal of time. Now, looking in the horizontal domain, in the vertical domain, we can talk about these waveforms in terms of their peak value, which again is just the positive maximum value. We can talk about these waveforms in terms of their negative peak value, which again is their minimum value. And we can also describe or quantify these waveforms in terms of their peak to peak value, which is simply the distance from the positive peak to the negative peak. But when discussing, quantifying these circuits, the y-axis, the vertical axis, will always be voltage or current. The x-axis will always be time or an angular value. Now, for the waveform sketched on the board, we see a sinusoidal waveform, or what we usually refer to as a sine wave. And let's suppose we're asked to calculate the voltage of this waveform at some particular angular distance in the waveform. And we are given that the maximum value is 10 volts and the minimum value is negative 10 volts. So instead of thinking in terms of this waveform with regards to its maximum voltage or minimum voltage, we want to think about this waveform that's continuously changing with regards to an instantaneous value. And when we talk about voltage or current as an instantaneous value, we need to change our symbol. So for the instantaneous voltage value, we will always use a lowercase v that I will always draw or write as a cursive letter so that we don't confuse it with the capital V. And if we're talking about current, then we will always use a lowercase cursive I to represent a value of current at an instant in time, at a snapshot in time, at a point in time of a continuously varying value. Now, to calculate this instantaneous voltage, we use this equation. The voltage, the instantaneous voltage equals V peak times the sine of the angular distance through one cycle. And the angular distance through a cycle is always represented with the Greek letter theta. Can you say theta? Good. So the voltage at an instant in time is the maximum or peak value times the sine of theta. So for this example, we have 10 volts times the sine of 45 degrees, which equals 7.07 volts. Now, try this with your calculator and make sure you get the correct answer. If you don't, there's a good chance that your calculator is in the radian mode and not the degree mode. So be sure that you set the mode of your calculator up in the degree mode, because your calculator doesn't know that this is a number in degrees unless you tell it. So if you just enter this as it's shown, 10 times sine 45, and hit enter, you should get 7.07. Now, we just looked at calculating the voltage at an instant in time given an angular distance through one cycle. But wouldn't it be nice if we could calculate the instantaneous voltage at a time value through one cycle? So given that one cycle is 16.67 milliseconds, let us calculate the voltage at the instant when this voltage is, or when time is at, let's see, that's 16 at 5 milliseconds. Now, the equation we just looked at said that V equals V peak times the sine of the angular distance theta. But we know that one cycle is always 360 degrees. And if I look at the relationship of theta to 360 degrees, that should give me the same relationship as little t is to big T, where 5 milliseconds is the little t, and of course 16.67 milliseconds is the big T. So for theta, I can substitute in that V equals V peak times the sine of parentheses little t over big T times 360 degrees, by simply rearranging this equation to solve for theta. So if I'm given the time of one cycle and the peak value, I can determine the voltage at an instant in time, such as 5 milliseconds. So again, when quantifying, discussing these AC waveforms in the vertical domain, the y-axis, I can talk about these waveforms in terms of their peak value, their negative peak value, their peak-to-peak value, and there's also times when I need to talk about this waveform with respect to the voltage at an instant in time. And this instant in time can either be an angular distance through one cycle, or it can be a time through one cycle, given the time of one cycle.